In this lecture, we discuss basics of probability, and we start with some basic concepts like experiment, sample space, and events. And so let's start with experiments. What do we mean by experiment? Experiment is an activity with observable results. For example, tossing a coin and observing the outcomes, tails or heads. So if we toss a coin, that's an experiment because the outcomes are observable. We only have two outcomes, either head or tail. So we can determine all possible outcomes. So in this case, we call this experiment. Now, if we are interested in finding all possible outcomes, we call that set that consists of all possible outcomes of an experiment, we call it sample space, and we denote it as S. So S is written as a set. It's a set, actually. So we write it as this set for this example head that consists of two outcomes, head or tail. Some books use omega to denote the sample space, but here in our book we use S, capital S. Now, if we are interested in some part of that sample space, for example, if we have numbers from 1 to 10 and we are only interested in even numbers, then we call that subset of the sample space, and the terminology that's used here is event. So we call that event. For example, for our experiment here, tossing a coin, the set that consists of one element, this is sometimes called singleton. This is an event. It's a subset of S, and the set or the subset that consists of T, tail, that's a subset of S. So this is what we mean by event. Now, since events are sets, I mean subsets, and subsets are sets, we can apply everything we learned about sets here, operations and properties. For example, we may define union of two events, intersection of two events, two or more events, complement. We can use Venn diagrams, and so on. Many things. Now let's start with example 1, the discussion about basics of probability. So if we have a rolled die, if we roll a die and we observe the number that falls uppermost, and we let that E is an even number, or the set of even numbers that are included here in this experiment, and F denotes or the event that consists of odd numbers. We want to find the sets E and F. The set E evens are 2, 4, and 6, because the whole sample space, if we want to determine the sample space, let's do part 5 here. The sample space is the all possible outcomes of rolling a die. So the outcomes are 1, 2, 3, 4, 5, or 6. Now, E is a subset of it. We are only interested in finding the even numbers. So the even numbers in the sample space are 2, 4, and 6. What about F? F consists of odd numbers. The odd numbers are 1, 3, and 5. Now, in part 2, we are interested in finding the intersection of the two events E and F. The intersection is phi. We don't have any elements in common. The union of the two events is everything in everything in F and everything added to everything in E. So 1, 2, 3, 4, 5, 6, and that's actually represents or equivalent to the set S. Now what is F complement? That F complement denotes all elements that do not belong to F but belong to S. So what are the elements from S that do not belong to F? F has 1, 3, 5, so the complement of that is 2, 4, 6, and that's actually the set E. Now if we want to use set Venn diagram to denote the sets E and F, first of all, we don't have anything in common between the two sets, so we graph them separately or as separate sets or disjoint sets. E and F, those are disjoint sets or disjoint events. We don't have anything in common, and here in this corner we write S to denote the sample space. Now elements of E are 2, 4, and 6, and elements of F are 1, 3, and 5. Now if we toss a coin 3 times and observe the sequence of heads and tails, we need to determine the sample space, all possible outcomes. So in this type of problems, it's better to make a tree diagram. So the first toss can give us either head or tail. If the first toss give us head, the second one can give us either head or tail. If the first one give us tail, the second one can give us head or tail. And if the first one and the second one are heads, the third one can be head or tail. If we have head, tail, then the third one can be head or tail, and so on. So we can find all possible outcomes. So we have sequences here of outcomes. Here we have head, head, head. Here head, head, tail. Here head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, tail. So we can write them using raster set notation. So we can write them here. So this is the sample space. Now we want to determine the event E that exactly 2 heads appear. So that should be a subset of S, of the sample space, where exactly 2 heads appear. So exactly 2 heads appear, that means this, this, and this. So we only have 3 outputs or outcomes: head, head, tail, head, tail, head, tail, head, head. Now part C, we want to determine the event F that at least 1 head appears. What does that mean? 1 head, or 2 heads, or 3 heads. That's what we mean by at least 1 head. At least 1, either 1 or 2 or 3. So what is the elements of the event F? 1 head, so that means we have tail, tail, head. We use different color here. 1 head here, 1 head here. So we have those 2 outcomes give us 1 head. So tail, tail, head, tail, head, tail. one hit. Now two hits, and actually there's another one, so we have here, I forgot this, so we have head, tail, tail, so three outcomes. Now two hits, we have this, this, and this. So we have tail, head, 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 tail, head, or head, head, tail. So this means two hits. Now we want to find the all outcomes that involve three hits, just one. Hit, hit, hit. So these are the elements of the event F, and as we can see, all elements of the sample space are included except tail, tail, tail. Now another example, if we roll a pair of dice, we want to write the sample space. Pair of dice, that means we may get one on the first die and one on the second die, or 1, 2, 1 on the first and 2 on the second, 1 with 3, 1 with 4, 1 with 5, and the last one, 1 with 6, or 2 with 1, 2 with 2, 2, 3, 2, 4, 2, 5, 2, 6. This means the first die has number 2 appear, and the other die can be 1 or 2 or 3, 4 up to 6, or 3, 1, 3, 2, 3 on the first die and 3 on the second, 3 on the first and 4 on the second, 3, 5 and 3, 6, and we continue in this manner until we exhaust all the outcomes. These are all possible outcomes, and these are elements of the sample space of the experiment of rolling a pair of dice. Now we want to determine the following events. E2 denotes the event that the sum of the numbers falling uppermost is 2. So that means E2 is, let's use this color, green color, to determine all outcomes that involve the sum of the numbers falling uppermost is 2. We only have one element here, or one outcome. So this is singleton set. Now what about E5? The sum should be 5. So let's use this color. Sum is 5. We have 3, 2, 2, 3, 1, 4, 4, 1. So we have the following elements. We have 1, 4, 4, 1, 2, 3, 3, 2. So we have 4 elements. Is there any other elements we left here? So 1, 4, 4, 1, 2, 3, 3, 2. and that's it. Now what about E8? The sum is 8. Let's use this color. The sum is 8, so we have 6 and 2, and 2 and 6, so the sum is 8, is only 2 outcomes, and so on. So we can determine any event of these this way. Now if you are interested in finding this, the event that represents the sum is greater than 7, for example, you can determine from this, or less than 4, we can determine it similar way. Now we come to the following section. We want to define probability. Now we talked about experiment, sample space, and event. Now we want to talk about the basic concept here, the concept of probability. What do we mean by probability? If you remember, when we toss a coin and look for the outcomes, possible outcomes, or the sample space consists of head and tail, and if the event E denotes the head, then what is the possibility or the probability of having head on the falling uppermost or on the uppermost on that die, or in that here we are talking about coin. So what is the possibility or probability of getting hit if we toss a coin once? So that means we have 1/2. The probability is 1/2. The possibility of getting hit is 1/2. And because we have one element out of 2 elements, so that's half of the outcomes. So here, if we want to find the probability of, or possibility, but we use the word probability here, probability of getting hit is number of heads is 1 over number of the elements of the sample space is 2. So the probability is 2. Now we can write this using some notation, probability notation. We can write P as probability of H, or the event is E in this case. So P of E is 1/2. Probability of getting head is 1/2. So what does 1 represent? 1 represents number of elements of the event, just one element, over number of elements of the sample space. We have 2 elements. So in general, probability of an event is number of elements of that event over number of elements of the sample space. This is the basic definition, or the basic formula for probability. Now we have some properties. Let me write them here of the probability. The first property is that any probability lies between 0 and 1. So it can't be negative. Probability can't be negative, can't be greater than 1, because we're talking about part of all, and that can't exceed 1, because we always have number of elements of the event, or number of outcomes that are that are represented by the event is less than number of elements of the sample space. So the numerator is always less than the denominator, and that means the probability is less than or equal to 1. Second, if E is S, if the event is S. For example, we may say here for this example that the event is getting head or tail. So getting head or tail, that means the event consists of head and tail, and that's equal to S. So number of E over number of S is, number of E is 2, number of S is 2, that's equal to 1. And in this case we call the event is certain event. Or certain probability. And we also have the following: probability of E plus probability of F is equal to 1 if E union F is S and the intersection is phi. So the union of the two sets is S. I mean, if this is S, that consists of the sets, let me write it this way, using Venn diagram. This is S, this is E, this is F, the union is the whole S. That means the probability is the probability of the E plus probability of F, and that's equal to probability of the whole S, which is 1. And this is very important. Probability of S is equal to 1, because if you want to find this, it's number of elements of S over number of element of S, and that means we have, so for our example here, 2 over 2, and that's equal to 1. Now if I ask you what is probability of phi of the set, the empty set, that's equal to number of elements of the empty set over number of elements of S. Number of elements of the empty set is 0, divided by number of S elements of the sample space. It can be any number. So we don't want, so 0 over that number is 0. So probability of phi is 0, probability of S is 1. Let's take an example. A fair die is rolled and the number of falls that falls uppermost is observed. Determine the probability distribution for the experiment. So this is, we have a fair die, so the sample space consists of 1, 2, 3, 4, 5, and 6. And we observed the number that falls uppermost. So we have the following event. 1, we may get 1, or 2, or 3, or 4, or 5, or 6. So if we make a table, and actually this table is called probability distribution, as we'll learn in the next chapter. So we have here the event and the probability. Now the first event is 1, getting 2, getting 3, getting 4, getting 5, or getting 6. And if the possibility of getting one element 1 is 1 over, because number of elements of this, let's call this event E1, this is E2, this is E3, E4, E5, and E6, 6 events. Number of elements of this event is 1 over number of elements of S. So n of E1, I'll do it just for the first event E1 and then just find it directly for the others. So probability here of the event E1 is number of elements of event E1 over number of elements of S. Number of elements of event E1 is just one element, over number of elements of S is 1/6. And that's correct also for the second one, the third one, the fourth one, the fifth one, and the sixth one. They have equal chance to appear or to occur. So these events are called simple events. Simple events are events that consist of only one element. Now let's take another example. We have a pair of fair dice is rolled, and we want to find the probability that the two dice show the same number. What does that mean? That means we have the following. The sample space is as before. This is the sample space of rolling two dice, and we have the event of getting same number on both of them, or both of the two dice. So we have E. The event E is, it's better to define it first. So we can write E is, or the event E represents that the fact that the two dice show the same number. So we define the event first, and then we find the elements of this, or members of this event, or the outcomes of this event. The same are 1 1, 2 2, 3 3, 4 4, 5 5, or 6 6. Now we want to find probability of E, of the event E. That's number of elements of E over number of elements of S. Number of elements of E, how many elements are there? 1 2 3 4 5 6, over how many elements are there in the whole sample space. There are 36, because if you remember from mathematical or counting principle, or mathematical counting principle, the first experiment, or the first step or task can occur in 6 ways, because we toss the first, or we roll the first die, and then we roll the second die. So we multiply the outcomes, we get 36 outcomes. So that's the sample, the size of the sample space, number of elements of the sample space, and then we simplify to get 1/6. Part B, we want to calculate the probability that the sum of the numbers of the two dice is 6. So we define the event, let's call it F. F is that the sum of the numbers of the two dice is 6. Now we try to find the elements of this event. 1 5, 5 1, 2 4, 4 2, and 3 3. And then we find the probability of F, that's number of elements of the event F over number of elements of the sample space. So we have 1 2 3 4 5 elements in the set F over 36, that's number of elements of the sample space. Now the third section talks about rules of probability. Any probability of any event is always greater than or equal to 0, and actually it's less than or equal to 1 as well for any event. And probability of S, as we described before, is equal to 1. And if E and F are mutually exclusive, and we mean by mutually exclusive, as we discussed in a previous video, that the intersection is phi. That means they are disjoint. If they are disjoint, then the probability of the union is the probability of F plus the probability of E. But in general, for any events E and F, whether they are disjoint or joint, or there's something in common, we have this general rule. Probability of the union is the probability of the first set. For example, here, if there's something in common between E and F. So we find the probability of E first. This is probability of E, this set, plus probability of F. And as you can see, this region, the common region, is considered twice. So that means if in order to find the probability of the union, we need to subtract one of the it was considered twice. That means we subtract one intersection. So the probability of the union in general is the probability of the first plus the probability of the second minus probability of the intersection of the two events. Now here we have some example. A school district has estimated the probabilities associated with the SAT verbal scores of students from the district. The results are shown in this table. If a student is selected at random, what is the probability that the student's SAT score will be more than 400? More than 400. Here, this, and this. As you can see, this is X. X represents the SAT score. And as you can see here, X is greater than 400 and less than or equal to 500. Here is greater than 500 and less than or equal to 600, and so the probability of getting more than 400, we can write it this way: probability of X is greater than 400, and that means we have probability of X between 400 and 500. Plus the second probability from 500 to 600, then the third, then the fourth. This means that we define how many events. We define 4 events. So probability of X greater than 400 is probability of X is greater than 400 and less than 500, less than or equal to 500. Union X is between 500 and inclusive 600. Union X from between 600 and 700 inclusive. Union X is greater than 700. And then probability of this is E1, this is E2, event 2, this is event 3, this is event 4. So the probability of the union is the probability, since those are disjoint, then we find the probability as probability of E1 plus probability of E2 plus probability of E3 plus probability of E4. What is the probability of E1? E1 means X between 400 and 500 inclusive, so that's the probability is 0.23 plus probability of E2 is 0.19, probability of E3 is 0.07, probability of E4 is 0.01, and the answer is 0.5, 1/2. For part B, the probability that the student's SAT score will be less than or equal to 500. So probability of X less than or equal to 500. That means less than or equal this event, and this event. So we can, instead of writing them as we did in part A, we can write them directly as probability of X between 400 and 500 inclusive plus probability of the event x between 300 and 400 inclusive, plus probability of x less than or equal to 300. And from the table, this is 0.23, this is 0.31, this is 0.19. The answer is 0.73. Now the SAT score is greater than 400 but less than 600. Greater than 400, that means here, and less than 600, that means here. So we have probability of x greater than 400 and less than 600 is probability of x greater than 400 and less than or equal to 500 plus probability of x greater than 500 and less than or equal to 600. So this probability is between 400 and 500 is 0.23. This probability is 0.19. So the sum is 0.42. Another example, a card is drawn from a well-shuffled deck of 52 playing cards. We want to know what is the probability that it is an ace or spade. So as we know that if this is the standard 52 playing card. So for example, here we have club, this is called club, and we have spade, we have heart, and we have diamond, with numbers from 1 to 10. And then we have jack, queen, and king here. So that means we have 13 on each row. We have 13 cards. So the sum is 52. 52 cards. Now the ace is this. The first one with one or single symbol is ace. This is ace. And so we have 13 clubs, 13 spades, 13 hearts, and 13 diamonds. And we have four aces. So if we denote by E, ace, and F, spade, because the problem asks us what the probability of that it's an ace or spade. If one card is drawn at random, what is the probability that it's ace or spade? So probability of E, or means union, and let me write it here. Or means union, and means intersection. So these are keywords that denote some operations when we deal with sets or probability. So E union F is probability of E minus plus probability of f. This is general. We have something in common between ace and spade because this can be ace and spade, minus probability of the intersection. This is called additive property of the probability. So what is the probability of E? I mean probability of ace. Probability of ace, how many aces are there? There are 4 out of how many elements or how many cards in this experiment? That's the number of elements of the sample space N of S. So that's 52 plus probability of F, probability of spade. How many spades are there? There are 13 spades. So this is 13 out of 52 cards minus probability of getting ace and spade. We only have one, that is ace and spade. This one is just 1 out of 52, and when we simplify we get 4 over 13. This is the probability, and as you can see this is less than 1 because the numerator is less than the denominator. Now let's talk about rules of complements. This is property 5. So the rule of complement is the following. We know that if we have the event E union its complement, those are mutually disjoint. E and E complement are mutually disjoint. Why? Because we don't have intersection between them. E means all elements of the event. E complement all elements that do not belong to the event. So those are disjoint. That means E intersected with its complement is 5. So E union E complement is actually equal to S, because if this is the sample space, this is E, so this is E, the set E. And what is the complement of this? This is the complement of this set. As we can see, the set and its complement, the union of the set and its complement gives us the whole S, the sample space. So now if we take probability of both sides, probability of E union E complement equals probability of S, but we know that probability of S is equal to 1. That's certain event. And what is the probability of the disjoint sets? It's probability of the first plus probability of the second, and we don't need to subtract the intersection because the intersection is phi, so the probability is 0. Now if we are interested in finding probability of E, this is 1 minus probability of E complement, because you can bring this to the right hand side, it becomes negative. So this is a basic formula. Now if we want to find probability of E complement, this, we can bring this to the other side, it becomes 1 minus probability of E. Those are called rules of complement. Let's take an example. The event E is such that the probability is 0.3. We want to find probability of the complement of this. Probability of E complement is 1 minus probability of E. This is 1 minus, what is probability of E? It's 0.3, so this is 0.7. And if we want to check our answer, we can add probability of E complement to probability of E, and that should give us probability of the sample space, which is 1. Now another example, a company manufactures TVs. The company found that 3% of the sets or TVs that are sold experience video problems, and 1% experience audio problems, and 0.0 or 0.1% experience both I mean the intersection, the common, and video and audio problems before the expiration of the warranty. We want first to find the probability that TV purchased by a consumer experience video or audio problems. And as we mentioned before, or means union. This is a clue for union. So we want to define events. We can define this as E. The event E is that the TV experience video problem, and we know that probability of E is we have for videos we have 3%. That means 0.03. This is a probability. When we see percentage, that means probability. But in the other problems, we are given numbers. Okay, so the second event is F. The TV's experience audio problem. So that means probability of F is how many? 1%. It's 0.01. Now both, that means the union. Both means union. Or sorry, intersection. Or means union. So both means intersection. So probability of E intersection F is 0.1%. So this is 0.001. 0.1%, this is equal to 1/10%, and that is 1/10 over 100. So we flip the denominator, we get 1/1000. Or you can use the calculator for this. Okay, so we want to find this probability. We want to find probability of either E occurred or F, either video problem or audio problem, and that's probability of E plus probability of F minus probability of E and F. So probability of E is 0.03, probability of F is 0.01, minus probability of the intersection is 0.001, and the result is, let me write it here, the result is 0.039. Let's do another or part B. What is the probability that a TV bought by a consumer will not experience video or audio problems? That means we want to find the probability that neither is correct. I mean E. If E, let me define E first, or let me define G, set G or event G, TV with video or audio problem, because we know the probability of this. The probability of this were found from the previous part, from the last part, from part A, or video problem or audio problem. That gives the probability of that is 0.039. Now we want to find the complement of that, because the problem says that the consumer bought a TV that will not experience video or audio problems before the warranty expires. So that means probability of G complement, and that's 1 minus probability of G. This is 1 minus 0.039. This is equal to 0.961. So this is the probability that the TV bought by a consumer will not experience video or audio or audio problems. The last example in this lecture is the following. We have two events, E and F, two mutually exclusive, and as we mentioned before, mutually exclusive, that means the intersection is phi. And suppose that probability of E is 0.1, probability of F is 0.6. What is the probability of the union? The probability of the union is probability of the first plus probability of the second. And we don't need to subtract the intersection because they are mutually exclusive. Probability of E is 0.1 plus probability of F is 0.6, and that's probability of 7. That's 0.7. And for part B, probability of the intersection, we know that they are mutually exclusive. That means the intersection is phi. Probability of phi is 0. Now, probability of E complement, using the complement rule, 1 minus probability of E, and that's 1 minus 0.1, that's 0.9. Now we have probability of E complement intersect F complement. How can we do this problem? This problem reminds us of De Morgan's laws. If you remember, E complement intersect F complement is E union F complement, or it's written backward. I mean, E union F complement, we can distribute the complement, but the union becomes intersection. And as you can see, this is equivalent to this. So I recommend you to review this part from the notes. So we have this is equivalent. So from this we find that this is the same as probability of E union F all complement. This is De Morgan's law. And this is 1 minus probability of E union F, applying the complement rule. So this is 1 minus probability of E union F. We already computed this in part A, so it's 1 minus 0.7, and that's 0.3. Now the last part is also the second part of De Morgan's law. We know that E intersect F complement, we can distribute the complement, but the intersection becomes union. So instead of writing this E complement F complement, we can write this using De Morgan's law as probability of E intersect F all complement. And using complement rule, this is 1 minus probability without the complement. And that's 1 minus, what is probability of E intersect F? It's 0.